In the silence beyond the planets, our machines drift farther than any voice tracing the edge of the sun's domain. Will we ever leave our solar system? Each section of this journey pulls us deeper through gravity plasma and light itself toward the oldest question of all: how far can we really go? If cosmic mysteries and interstellar dreams ignite your curiosity, hit like subscribe for more voyages beyond the stars and let your mind drift with us into the unknown. The sun sits in a quiet arm of the Milky Way, not at the bright centre and not at the fragile edge, but in a suburb of stars threaded along a spiral lane of dust. Around it stretches a cavern of thin gas called the local bubble, a low-density pocket carved by ancient supernovae, whose shock fronts swept the neighbourhood clean and left wisps of hot plasma in their wake. In this cavity, the normal clutter of interstellar space thins to a breath, and the solar wind inflates more easily, pushing outward like an invisible weather front. The scene is not static. The galaxy itself wheels slowly, and the sun drifts with its family of planets around the grand centre on a path that takes hundreds of millions of years to complete. On human timescales, the motion is almost still, yet it never stops. The solar system is a moving island in a moving sea. The large-scale environment sets the first terms for any dream of leaving. A spacecraft does not fly into emptiness. It flies into the texture of the interstellar medium, the thin gas and dust between stars. Here the local bubble matters because it lowers the pressure outside the heliosphere, the bubble carved by the solar wind. The size of that bubble, the shape of its magnetic skin, and the strength of the boundary all respond to what the larger galaxy presses upon it. When ancient stars exploded nearby, they did not erase the medium so much as sculpt it, and their fingerprints remain. Maps of soft X-rays of ultraviolet glow and of polarized starlight trace the rough edges of this cavity, and hint at folds, spurs and tunnels where the bubble meets denser clouds. The sun does not rest at the bubble's centre. It is offset, parked near the edge of a warm, partially ionized smear called the local interstellar cloud. That cloud is not a fog bank with crisp borders. It is a drift of atoms and magnetic threads a few light-years thick, with density low enough that a single grain of dust might wander for years without collision. The solar system is either inside this cloud or skimming its edge, depending on where the measuring instruments look and when they look. The subtlety of that placement matters. If the sun presses into a slightly denser patch, the pressure outside the heliosphere rises, cosmic rays bend in new ways, and the frontier moves closer. If the sun passes into a thinner patch, the boundary relaxes outward. A line that marks leaving can slide back and forth by distances measured in the journeys of decades. Around this local structure runs the framework of the Milky Way. The sun orbits within the Orion Spur, a minor arm between grander lanes. Above and below the galactic plane, the density of gas and dust changes, and the solar system bobs over long timescales, like a buoy crossing a slow swell. The galaxy's magnetic field threads through this scene not a simple bar, but a tangled weave with directions that change across scales. Where the solar wind meets that field, currents and reconnection events can twist the edge of the heliosphere into shapes that look less like a symmetrical shell and more like a cometary droplet with folds and ripples. Each ripple can redirect the path of a charged particle and complicate the clean idea of a single boundary to cross. The neighbourhood also hosts the Gould Belt, a ring-like arrangement of young stars and gas clouds tilted with respect to the galactic plane. Its star-forming regions shine as familiar constellations to human eyes, but to spacecraft and to charged particles they form regions of different radiation and wind histories. The history of nearby supernova inferred from isotopes found in ocean crust and from the ages of the belt's clusters suggests that in the last few million years, Explosions occurred at distances close enough to rattle the bubble. Each event would have sent shock waves through the medium, thickening some zones and thinning others. The solar system moves through the remnants of those waves. Therefore, even if human craft became fast enough to approach the edge in years instead of generations, they would still meet a boundary that is weathered by ancient storms. The scale of the local bubble is large by human measure, hundreds of light years across, yet small in the galactic sense. It sits inside larger features like cavities carved by associations of hot stars and the broader spiral arm flows. This nesting of structures means that any path outward eventually crosses layers each with its own rules. Today, the Voyagers have begun to sample the interstellar medium's particles and fields just beyond the heliopause. Their readings tell of a denser and colder plasma than expected, and of a magnetic field that rotates less abruptly than many models predicted. Those details fold back into the picture of the neighborhood and hint at hidden scaffolding. Perhaps the local bubble's wall pushes in with a gentle hand. Perhaps the interstellar magnetic field drapes around the heliosphere in sheets. Perhaps the density is patchy on scales that match the size of the solar wind zone fluctuations. Such maybes are not decorative. They decide how smooth or rough the road is as one tries to leave. To ask whether the solar system can be left is to ask where the solar system ends. If the boundary is a sheath that moves with solar cycles, with interstellar turbulence, and with the sun's slow drift through clouds, then leaving is not a single gate, but a series of gates, each opening and closing on different timescales. Beyond the heliopause lies the wider local bubble, but farther still lies the frontier of denser material in other nearby clouds. If the sun's path takes it toward a cloud with higher pressure, the heliosphere may shrink in centuries or millennia, bringing the frontier inward and changing how future craft will climb the slope out. If instead the sun glides into a thinner corridor, the heliosphere could swell and the threshold would recede like a tide. This perspective reframes the guiding question. The barrier is not only distance or speed, but also context. A mission that leaves today does so into a slightly different sea than a mission that leaves in 1,000 years. The navigation problem thus begins with a map of the neighborhood's physics, a map that is still incomplete. Instruments on space telescopes and at the edges of the heliosphere continue to draw that map in faint strokes. The more it fills, the more one sees places where the medium is knotted or smooth, and where a path might be easier or harder. Perhaps there are corridors where magnetic fields align in ways that let charged dust and plasma streams guide a craft, or regions where turbulence would batter a sail. Perhaps, too, there are ancient shock fronts that still carry memory of the supernova ester that birthed this bubble fronts that a future probe could surf to gain an infinitesimal push. In this opening view, the solar system is a set of nested shells and moving boundaries situated in a carved-out chamber of the Milky Way. The sun's wind swells within the local bubble, and the local bubble itself is a scar in a broader arm shaped by long dead stars. The edge to cross is shaped by both. To dream of leaving is to first see that the edge is alive, that it breathes with the galaxy, and that it has a history. Each observation from a tilt in polarized starlight to a count of high-energy particles adds another brushstroke to the neighborhood's portrait. The mystery is not whether an edge exists, but which edge matters, how it shifts, and how a craft can sense and slip through it with grace. The path outward begins here, in a place already marked by departures. The matter that once filled this space was blown away. What remains is quieter but not empty, and it waits to be read. The sun does not sail through a uniform ocean, but through a quilt of clouds stitched from warm atoms, cool filaments and magnetic threads that wander like drifting kelp in a gentle tide. Astronomers call the nearest of these the local interstellar cloud, a region of thin, partly ionized gas, a few light years across, cushioned by the broader emptiness of the local bubble. The solar system moves through this patchwork at tens of kilometers per second, and that steady drift changes the pressure on the heliosphere, the great bubble blown by the solar wind. The boundary between solar space and interstellar space is thus a living membrane. It expands and contracts not only with the 11-year pulse of solar activity, but also with the slow approach of denser or more magnetized interstellar parcels. The reality of this breathing edge emerges from measurements that seem almost impossibly delicate. Spacecraft sniff neutral atoms that wander in from outside count grains of dust as they tap detectors and trace the directions of magnetic fields by watching charged particles bend. The Ulysses mission, looping over the poles of the Sun, charted a flow of interstellar helium that slides through the solar system like an unseen wind, and that flow's slight change in direction over years suggested that the cloud outside is not a smooth hallway, but a corridor with eddies and seams. Interstellar Boundary Explorer drew wide-angle maps of energetic neutral atoms that leak from the frontier, revealing a ribbon-like band brighter than expected, as if the draped galactic field lines and the shape of the heliosphere conspired to focus signals along a great arc. Voyager instruments, now sampling the medium beyond the heliopause, hear faint plasma waves and register cosmic ray fluxes that rise and fall with variations in the surrounding density. Each dataset points to the same conclusion: the Sun moves through rooms with different air, and the walls of the solar bubble flex to fit. In this scene, the local interstellar cloud is not the only actor. Nearby lurk other named streams such as the G-cloud, and fragments sometimes described as ripples, and the borders between them are fuzzy. The Sun could be skirting a boundary between cloudlets, with one side slightly denser or differently magnetized than the other. Even a small change matters when the ambient densities are so low that a cube the size of a house holds only a handful of atoms. At such rarefied levels, the magnetic field takes on outsized influence, shaping the path of ions guiding currents, and storing energy that can be released in sudden reconnection events. The outer skin of the heliosphere meets this field not as a smooth sphere, but as a malleable surface with folds that can wrinkle under stress. When the Sun turns active and throws coronal mass ejections outward, those waves crash against the frontier and push it outward, but the response depends on the stiffness of the field outside. A stronger interstellar field resists a weaker one yields, and the result is a boundary that migrates by distances measured in astronomical units over the course of a solar cycle, and by even greater margins over centuries as the Sun threads new cloudlets. For the question of leaving this slow migration matters, because it changes where a craft meets true interstellar plasma, and how long it cruises within the sheath of the Helios heath, where shocked solar wind flows sideways. A probe hurried by, gravity assists might reach the heliopause sooner when the heliosphere is shrunken, while a mission in a time of outward swell must traverse a wider region of disturbed space. Even the direction of travel can matter, since the heliosphere seems asymmetric along the direction of the interstellar flow and the local magnetic field. Paths that aim upwind could strike a thinner frontier than paths that slide downwind, where a comet-like tail may stretch for hundreds of astronomical units. The very meaning of outside thus depends on a moving context. The mystery deepens when the measured flow of interstellar atoms shifts slightly in angle or speed over decades, hinting that structures a few light years away are not static but drifting. Some models place the solar system near the ragged edge of the local interstellar cloud, possibly entering a corridor of lower density, or perhaps pressing into a lump of higher pressure. If the latter is true, the heliosphere of future centuries could shrink, squeezing planetary space and letting more high-energy cosmic rays wander inward. Geological clues suggest that such changes have happened before. Layers of ocean crust contain rare isotopes that could have been sprinkled by nearby supernovae a few million years ago events that likely dented the local bubble and sent compressions through the clouds. If a shock front passed through, the heliosphere would have been forced inward and then allowed to relax as the wave moved on. A spacecraft born in that era would have faced a very different frontier. Instruments today attempt to measure the present state in finer detail. The dust detector on Cassini orbiting Saturn counted interstellar grains and found that many are pushed away by solar radiation pressure and magnetic effects, yet some penetrate their trajectories, bending in ways that betray the changing electric fields of the solar wind. The New Horizons spacecraft, coasting through the distant Kuiper belt, carries a detector sensitive to the glow of interplanetary hydrogen, and thus to the balance between solar output and incoming interstellar gas. Together, these observations sketch a portrait of a boundary that answers to forces on multiple scales, from daily space weather to million-year galactic tides. Such a dynamic backdrop has practical consequences for design. A beamed sail might prefer to launch when the heliosphere is high and the hydrogen wall taut, seeking a cleaner break from solar plasma. A fusion-driven craft might be indifferent to a few astronomical units of difference, but could care deeply about the direction of the interstellar magnetic field if its charged exhaust interacts with ambient lines and creates unwanted drifts. Navigation software would need to ingest current measurements of neutral atom flows and field orientation, then update trajectories not only by gravity but by drag and magnetic coupling. Even the shielding strategy shifts with context. A stiffer outside field can funnel more galactic cosmic rays around the heliosphere, lowering background radiation inside, while a softer field allows slightly more to wander inward. A mission staged for departure at the wrong phase might thus expose crew and electronics to a marginally harsher environment for years. The uncertainty is not a barrier to progress so much as an invitation to read the medium more closely. Every interstellar atom that slips past the sun carries a message about the room beyond the door. By stacking many such messages, a patient picture forms. The local interstellar cloud has gradients. Its temperature and ionization are not uniform, and the direction of its drift relative to the sun is shifting by small increments that nonetheless matter over mission timescales. The idea that the solar system can be left as if stepping from one room into another gives way to a slower image. The door is a curtain that billows. One does not pass through once, but passes through a thickness whose shape changes and perhaps passes through again as the sun itself enters a new patch of the wider quilt. The suspense sits in the time mismatch. Spacecraft progress on the scale of decades while the cloudscape evolves over centuries and millennia. A launch in this century will meet one version of the boundary. A launch in the next may meet another. And yet within this motion there may be gentle corridors to exploit. If the interstellar field lines drape in a way that softens the upwind nose, departures along that axis could find a thinner sheath. If a region of lower density approaches from the direction the sun is already moving, the heliosphere could relax and give future missions a slightly longer reach before they touch true interstellar plasma. The local interstellar cloud and its neighbours thus do not simply surround the solar system, they collaborate with it in shaping the threshold. To ask whether we will ever leave is to ask how we will time and aim the crossing of a border that listens to both the sun and the galaxy. Each new map, each count of atoms, each tweak to the measured flow adds a stitch to the quilt and reveals that the fabric ahead is not a wall but a moving weave, Long before a probe crossed the heliopause, the solar system let slip signs that it is not a sealed world, but a permeable archipelago where the outside sifts in by many paths. The first hints arrive as a faint glow, a soft wash of ultraviolet light from hydrogen, that drifts between the stars and scatters the sun's rays, a subtle sky-wide sheen that early space telescopes and sounding rockets notice when they look for darkness and find a whisper of brightness instead. The pattern of that glow bends around the sun brighter in a cone downstream of the solar motion and dimmer upwind as if an invisible breeze were shaping an unseen fog. Within that fog, neutral helium flows more stubbornly, because radiation pressure pushes less on it, and so it threads the planetary orbits with greater faithfulness to the interstellar wind. Instruments aboard spacecraft such as Ulysses build a map of this helium river by counting atoms that slip through tiny apertures and leave ions in their wake, and the map reveals a focusing cone that forms behind the sun, the gravitational lensing of a gas at speeds of tens of kilometers per second. This is the first clear signature of the outside moving through our rooms, and it carries the scent of temperature, density, and direction, in ratios of species and in the angle of the flow. When these neutrals meet sunlight or brush past solar wind protons, they often lose electrons and become charged, suddenly feeling magnetic fields that once let them pass. They turn into what scientists call pickup ions, newborn particles that spiral and surf on the solar wind their energies and pitch angles, betraying the place and time of their birth. Spacecraft near Earth orbit at Saturn, and in high-latitude solar paths detect these pickup ions as an extra population sitting on top of the usual solar wind, a quiet influx of outsiders transformed into insiders by ionization. The pattern of their arrival changes with the solar cycle, and with the sun's tilt teaching that the influx is not steady, but modulated by the star's own weather. Each detection draws a curtain back. The solar system is not merely bathed in outside gas, it is threaded by a constant thread of atoms and dust that slides through with barely a collision. Dust grains are larger messengers. Interplanetary probes carry impact detectors that count and weigh the microscopic grains by the electric shock they produce upon impact. When the counts are plotted against direction, a steady stream appears that does not align with known comet trails or asteroid debris. Its speed and approach angle match the helium wind, and its seasonal variations follow the geometry of the solar system's motion through that stream. The grains are not all deflected or burned away by sunlight and by the solar magnetic field. Many are turned aside, but a fraction penetrates deep, how deep, depending on their sizes and on the phase of the solar cycle. During times of stronger solar magnetic fields, more grains are excluded. During quieter times, the gate opens wider. Decade by decade, the in situ detectors reveal that the solar system breathes interstellar dust, a slow inhalation, and exhalations synchronized to the sun's moods. The third kind of messenger arrives as energetic neutral atoms, born when fast solar wind ions steal electrons from cold interstellar atoms and thus lose their charge. Uncharged, they care little for magnetic fields and travel in straight lines, carrying information about the interactions at the boundary. When a small spacecraft in Earth orbit begins to image the sky in this energy range, a ribbon appears, a great arc of enhanced emission that circles much of the sky and refuses to match any simple prediction. It looks as if the draped interstellar magnetic field and the shape of the heliosphere together focus these neutrals a lensing by fields rather than gravity. This is not the first trace from outside, but it is a map drawn by the combined hands of inside and outside, and it tells that the frontier is a place of alignment, tension, and release. Comets and meteor radar echo another story. Most objects that streak across the sky follow bound paths within the solar system, but a few exhibit orbits that are hyperbolic with speeds that cannot be explained by planetary kicks. Many such cases are measurement errors or the debris of comets that have been perturbed, yet the possibility of true interstellar meteoroids remains, and radar surveys seek them with patient statistics. In one or two cases, signals hint at grains moving too fast and at angles that fit no local parent body. Later, the arrivals of a cigar-shaped visitor, and then a comet with deep space chemistry, confirm that larger bodies can wander in across the planetary lanes and leave again without greeting. They are rare, but their mere presence turns the solar system into a place without a hard wall, a square that drafts through traffic on an interstellar highway. The evidence gathers across scales. At the smallest individual atoms sweep through and become pickup ions whose distributions record wind direction and temperature. At the middle, dust streams wax and wane as the solar magnetic shield flexes. At the large edge, neutral atom images sketch the frontier's unevenness. Together they imply that the boundary is not a barrier, but a membrane, across which information and material pass both ways. Even the composition of the interplanetary medium carries fingerprints of the outside. Ratios of noble gases, the fraction of neon versus oxygen, the presence of certain isotopes and the slight enrichment of heavy elements in pickup ions hint at the chemistry and history of the nearby clouds. When the sun moved through different neighborhoods in the recent past, the mixture likely changed as well, and traces of those passages may sit frozen in polar ice or embedded in micrograins collected by high-altitude aircraft. On human timescales, the measurements show that the flow direction of helium has shifted by a small but noticeable angle over a few decades, suggesting that the sun is sliding along a gradient or skirting a boundary within the local cloud. Such subtlety matters when planning any path outward, because the best exit lane may lie along a direction where the sheath is thinnest or the external field is most favourable. The notion that the solar system is already porous reframes the guiding question. Leaving is not the first contact. The first contact has been happening all along, a slow exchange that has written itself into data from many missions. Pioneers carried ultraviolet instruments that saw the hydrogen glow. Later probes sniffed helium, and dust ringed planet orbiters, counted grains and found interstellar angles. Polar sun orbiters traced out the high latitude flow, and edge riders like the Voyagers now taste the plasma beyond. Each mission adds a layer, and some layers contradict first expectations. The neutral hydrogen glow pulses with solar cycle changes more strongly than assumed. The dust flow bends in response to magnetic fields with a seasonality that reveals subtle drifts. The pickup ion energy distributions exhibit features that point to transient waves or to clumps in the incoming flow. The outside is not smooth, and its roughness can be felt from within. In this picture, the solar system behaves like a set of nested sieves washed by a diffuse river. The largest holes let pass only the most indifferent neutrals and the most determined grains. The finer meshes within are the magnetic structures that sort by charge and phase of the solar cycle. The smallest sieves are the detectors themselves, tiny funnels that capture messages one atom at a time and decode them with patient counting. This is how the first traces arrive, not as a shout, but as a hush that grows in confidence as measurements align. The suspense deepens because each alignment raises a new question. If the helium flow direction changes by a fraction of a degree, what boundary lies ahead or behind to steer it? If the neutral atom ribbon brightens, what twist at the heliospheric edge has tightened to focus it? If dust counts fall for a few seasons, what folds in the solar magnetic field have stiffened the shield? The outside is already inside, and the map of its entry points is the first chart for any future departure. In recognizing the traces one sees that leaving will not be the first time a craft meets the interstellar medium. It will be the first time it does so by design. In the early 1970s, 2 small craft leave Earth on paths that will bend around the giant planets and then keep going. They are called Pioneer 10 and Pioneer 11, and they are simple by later standards, spin-stabilized dish-faced armed with cameras, particle counters, magnetometers, and a bright optimism that a clean design can read a dark frontier. They carry plaques that show a map of pulsars and a human figure, a modest message intended for no one in particular. But the real message they carry is the pattern of their motion. Their trajectories are read by the deep space network as shifting tones, the Doppler pulses that turn distance and speed into music for engineers who measure whispers in long arcs. As the craft swing past Jupiter and one of them by Saturn, the gravity of those worlds leans their paths outward and the sun's hold loosens. They do what few things have done before they take the long road toward the edge. Along this road a puzzle grows. After careful accounting for solar radiation pressure, for the faint drag of the solar wind, for the pressure of the radio beam leaving the dish, and for the known gravity of planets and belts, the craft seemed to feel a tiny additional pull. It is directed roughly toward the sun, not strong enough to change the overall path in a dramatic way, but steady enough to raise eyebrows. The Doppler data show that the tone drifts a little faster than expected, as if the speed along the line of sight is being shaved by a constant gentle hand. For years, analysts test each assumption. Could propellant leaks be bleeding out, giving a minuscule push? Could a flaw in clock standards create an illusion of acceleration? Could the pressure of light from the sun be misestimated because the surface of the craft has aged or darkened? Each possibility explains a part but leaves a residue. The residue becomes a named thing, the Pioneer anomaly, a reminder that in the quiet outside Planet 9 and Planet 10, even a postcard weight of force matters when integrated over years. The anomaly becomes part of the law of leaving because it teaches that precision in the deep is as much art as math. At the Jet Propulsion Laboratory and at partner institutions, teams build thermal models of the spacecraft. The radioisotope thermoelectric generators glow with waste heat, and the electronics boxes warm during operation. Heat leaves in infrared photons, and if that heat departs in a slightly uneven way, it can add up to a net push, a recoil akin to a whisper of steam leaving a nozzle. The crafts are not symmetrical in every detail. The dish faces forward, the booms and boxes hang outward, the generator fins sit off to one side. If more warmth is radiated in one direction than in the other, the craft will feel it. Analyses sharpen archival telemetry resurfaces, temperatures and power levels are reconstructed, and the models show that the thermal recoil is large enough and oriented correctly to account for most, perhaps nearly all of the steady tug. The mystery does not vanish so much as resolve into the calm lesson that the deep is sensitive to everything. A what here, a reflection there, and the long arithmetic of years sums the small into the perceptible. The pioneers have other puzzles to share. Their particle detectors count the changing rain of cosmic rays and solar energetic particles as the solar cycle swells and fades, offering early hints that the bubble carved by the solar wind has a structure that will matter later to the voyagers. Their magnetometers trace fields that whisper of currents carried outward and folded back, and their images of Jupiter's intense magnetosphere reveal a system so rich that the second craft is retargeted to risk a near pass by Saturn's rings. In a planetary sense, they are scouts, but in the question that frames this story, they are pathfinders. For the idea that leaving is a long conversation with tiny forces, The careful accounting that turns their Doppler tones into motion lays groundwork for all later missions that dream of speed and distance. If a beamed sail hopes to ride a tight ray of photons out of the heliosphere, it must know how the sail heats and re-radiates, how even a small wrinkle will give off light unevenly, and how that uneven glow will bias the trajectory over years. If a fusion pulse craft kicks at measured intervals, the cumulative jitter will matter, and any persistent thermal bias from hot radiators will add a background push. If a thin probe hurries outward with the nuclear battery warming one side more than the other, the tone of its departure will drift unless the design channels heat carefully. The Pioneer episode becomes a quiet teacher. The environment of interplanetary space is so clean that engineering flaws turn into celestial mechanics. It also reframes trust. The anomaly spurred some to wonder about modified gravity or overlooked masses in the outer belt, but the eventual thermal accounting suggests that the first suspicion should remain with the emissary and its habits. This does not belittle the mystery, it honours the medium. The path out is a perfect laboratory in which the smallest thrusts are not swallowed by drag. It is a mirror where the craft sees itself moving. The pioneers also hint at the practical reach of gravity assists for leaving. Their encounters with Jupiter, and for one with Saturn, show how falling toward a planet and then outrunning it can give speed for free speed measured not in short bursts, but in enduring additions to the journey. They do not achieve the fastest exits of later craft, but in spirit they show that the solar system's own masses can serve as stepping stones. The discipline that interprets their motion becomes the discipline that plans inward dives for outward gains, the Oberth maneuvers that later sections will explore. There is a gentler lesson too in the way the anomaly was pursued. It took patience, archival work and cooperation across agencies and decades. The detective story was not flashy, but it was essential for confidence. A future mission that aims to reach hundreds of astronomical units in a human lifetime cannot afford to be blind to the drift caused by its own heat. Navigation models must include the thermal recoil, the nuclear power decline, the changing emissivity of surfaces in space weather, and the soft shove from the faint radio beam used for communication. Each whispers at the level of the Pioneer tug, and in the deep those whispers accumulate. As for the plaques bolted to the frames, they are not the only messages. The larger inscription lies in the data that the Deep Space Network listened to for years, the long tones that told a story of courage, imperfection, and correction. Leaving is not only a contest with distance, it is a test of whether one can hear the small voice of the craft over the large silence of space. The anomaly helped tune that ear. It also deepens the sense that the solar system is not a simple stage. The small tug that seemed to pull sunward reminds that our definitions of force and friction must include the spacecraft itself as a source. In a region where the solar wind thins, where dust counts are low, and where photon pressure is gentle, the vehicle becomes its own weather. The sun still holds, but the craft speaks back through the warmth of its own body. This reciprocity sits at the heart of all plans to leave. The design of engines, the layout of radiators, the choice of materials, the frequency and power of communication, the spin or three-axis control, all translate into subtly different paths over decades. The pioneers make that translation visible. They wander outward until their power dwindles and their voices fall below hearing. Long after their paths continue inertial and indifferent, carrying the plaques toward the stars. The question of whether we will ever leave is not answered by them, but it is clarified. We will have to leave with a craft that knows the taste of its own heat and the sound of its own beam, and that can fold those self-made forces into a path that holds true. The first lesson of departure is to look inward at the little physics we carry with us, because the outside can be so clean that it makes our inner traces the main wind. In the late 1970s, 2 spacecraft rise from Earth on long arcs that will become the most far-reaching journeys ever made. They're born modest, each no larger than a car, each a lattice of struts, dishes, booms and instruments designed for patience rather than haste. Their strength is not brute thrust, but a choreography that begins decades earlier, when celestial mechanics experts noticed that the giant planets will line up in a rare pattern. This alignment happens roughly once every 175 years, a slow parade in which Jupiter, Saturn, Uranus and Neptune pass in a sequence that allows one traveller to visit them, in turn gaining speed at each encounter by borrowing a little from their motion around the Sun. The trick is not magical. A gravity assist is a careful fall into a planet's well, and a measured climb out exiting with a change in direction and speed that from the Sun's point of view counts as free energy taken from the planet's vast store of orbital momentum. Voyager 1 and Voyager 2 are built to ride this dance. They leave in 1977 on slightly different paths. Voyager 2 aims for the whole chain, a slow relay that will stretch across a dozen years. Voyager 1 takes a steeper route that prioritizes a close pass by Saturn and its largest moon to throw the craft northward out of the plane of the planets on a fast escape. The Deep Space Network listens as the tones slide and confirms that calculations match reality. Each planetary swing is both a destination and a lever, a world to study and a handle to pull. At Jupiter, the first great leap occurs. The planet's huge gravity well pulls the craft inward. As they skim past the craft, absorb momentum from a world that itself circles the Sun with regal speed. The payback is physics without fuel, a boost that turns the outward climb into a long glide. But the gravity is not the only spectacle. Instruments reveal a magnetosphere so large it sweeps the space around it into a storm of charged particles. A small world named Io erupts with volcanoes that spray sulfur and sodium into a torus that glows in ultraviolet light. The Great Red Storm shows complex shapes. The ice moons carry ridges and fractures that suggest buried oceans. None of these wonders were guaranteed. They arrive because the path to the edge requires a close dance with giants, and the dance reveals that leaving is also learning. The crews guiding the craft thread needles. To gain the right turn at Saturn, Voyager 1 must pass at a precise distance behind the planet, timing its swing to aim toward a meeting with the moon Titan. Titan's thick atmosphere, seen in the dim orange light, helps fix the path that will tilt the trajectory out of the planetary plane. The price of this decisive turn is that the craft will not then be well placed to continue to Uranus or Neptune. Voyager 2, by contrast, takes gentler bends that preserve the chain. Years later, after a deep space coast, it slides by Uranus, a world tilted almost on its side with a magnetic field that is offset and twisted in ways that defy simple models. The moons show unexpected terrains, especially Miranda scarred as if shattered and reassembled. The rings faint and knotted teach that even small shepherding forces can sculpt matter into narrow bands. The craft then sails on toward Neptune, where a blue world with fast winds and a dark storm waits at the edge of known planets. The flyby reveals Triton, a moon with geysers of nitrogen that wreath the surface, a sign that even in deep cold there is energy and motion. Each of these worlds is a stepping stone, but each encounter also writes a chapter in the craft's momentum ledger, turning modest launch energy into an escape that no rocket alone could easily give. The elegance of these arcs is that the energy gained is permanent. After the last assist, there is no engine burning, no propellant left to push only the faint shove of sunlight and the whisper of heat from the nuclear battery. Yet the glides continue because the planets have shared a fraction of their motion. From the Sun's perspective, the voyagers now move on paths that will not loop back. They are on escape trajectories that climb above and beyond the family plane toward the border, carved by the solar wind. The speed is not close to light, not even a large fraction, but it is steady a few tens of kilometers per second enough that over decades the distance mounts into many tens and then over 100 astronomical units. Along the way, the instruments keep listening. The magnetic field sensors trace the curls and folds of the solar wind as it thins. The plasma wave instruments hear faint songs when charged particles vibrate in the medium. The cosmic ray detectors watch the balance between particles born in the solar storms and those arriving from the galaxy. As the craft reach the outer realms, they feel a change. The solar wind, once supersonic in the local plasma sense, slows at a termination shock and spills into a turbulent region called the Helios Heath, where it turns sideways and struggles against the pressure and the magnetic field of the interstellar medium. The probes coast through this uneasy zone for years. Later, the data show clean markers that the boundary has been crossed. Particle counts shift, plasma densities change, magnetic field strength rises, while its direction alters less abruptly than some expected. Voyager 1 crosses the heliopause in the year 2012. Voyager 2 follows in the year 2018 on a slightly different path, and reports a boundary with different pressure and temperature proof that the edge is not a perfect shell but a rough living frontier. The grand leaps that began at Jupiter have ended at the threshold of interstellar space, and the last push was not a burn but a gravitational gift given decades earlier. The intrigue lies in how a careful use of planetary motion made this possible. The idea of the Oberth effect, which says that a burn done deep in a gravity well yields more useful energy, because the craft already moves fast, lurks behind later plans to dive close to the Sun for speed. The Voyagers did not perform extreme burns, but their paths taught mission designers to think of the solar system not as a barrier, but as a machine, a set of gears whose teeth are planets and whose lubrication is gravity. Free energy is a misnomer, but the metaphor holds there is energy available if one knows where to take it from without paying much. The price is timing, precision, and patience. The precision required discipline, and the patience spanned decades of cruise between encounters. The reward is not only distance, but knowledge about the structure of the outer regions that will shape any future exit. The magnetic draping measured beyond the heliopause suggests that sails or plasma engines may behave differently there than near the planets. The distribution of energetic particles at the edge tells designers how much shielding a human habitat would need, and for how long. The very fact that one crossing felt denser than the other implies that routes outward may encounter different thicknesses of frontier depending on direction and solar cycle. The Voyagers now drift in the local bubble, still hearing plasma vibrations faintly, when a solar outburst sends a pressure wave that reaches them years later. Their power falls year by year. Instruments go silent to preserve the few that matter most for the interstellar medium. Yet the message of their flight remains bright. Modest machines launched with the rockets of their time used the dance of planets to become interstellar emissaries. They did not rush, they were carried, they did not conquer. They collaborated with celestial mechanics. In their wakes they leave a template. Future craft that hope to leave faster can still trace a path that falls inward first for a deeper speed that steals gently from the moving giants and that emerges poised for a long coast. The free energy hidden in planetary dance is not an extravagance. It is a quiet account that pays out to those who keep time with orbits and who accept that leaving is not always a straight line. It is a sequence of steps taught by the giants themselves, and each step brings the edge a little closer. The edge is not a line painted in space, but a thin and restless sheath where the sun's dominion ends and the galaxy's weather begins, and yet when a craft passes through it, the change feels like a door. The heliopause is that door, and for the first time instruments have sensed it from the inside and then from the other side. The story builds over years as each voyager coasts through the heliosheath, the region of slowed and heated solar wind beyond the termination shock where plasma swirls and magnetic folds drift like kelp in a tide. Here the solar wind that once raced outward at supersonic speeds in the local plasma sense has been shocked, compressed, and turned sideways by the pressure of the interstellar medium. Particle counters see a shifting balance. Solar energetic particles fade with distance, while higher energy cosmic rays born in distant supernova remnants and accelerated by tangled galactic fields increase. The cosmic rays do not respect the solar magnetic field as easily as lower energy particles. They wander in from the outside with a stubbornness that grows as the shielding weakens. The crossing arrives first for Voyager 1 in the year 2012, not as a trumpet blast, but as a set of signatures that layered together leave little doubt. Low-energy charged particles, the kind tied to the solar wind plummet. High-energy galactic cosmic rays jump. The magnetic field strength steps upward, yet its direction does not swivel dramatically as some models had predicted, an intriguing hint that the interstellar field drapes around the heliosphere in a way that preserves direction across the interface. A plasma instrument that could have tasted the density directly had failed decades earlier, but the craft carries an ear more subtle. Its plasma wave detector listens for faint radio-like vibrations. When a solar outburst sends a pressure wave outward, and that wave eventually plows into the plasma beyond the heliopause, it excites oscillations whose tone depends on the electron density of the medium. Months after the suspected crossing, such a ring reaches the craft, and the measured tone corresponds to a density several times higher than that of the heliosheath, a value expected for the interstellar plasma in the local bubble. This delayed chime acts like a flare, revealing the water level on the far side of a reef. The combination of particle counts, magnetic field strength, and plasma wave tone becomes the certificate of passage. Voyager 2 crosses in the year 2018 on a path and at a solar phase different enough to enrich the comparison. This time, a functioning plasma instrument feels the density jump directly. The solar wind speed drops towards zero at the boundary. The temperature falls from the hot heliosheath to a cooler yet denser plasma beyond, and the magnetic field strength again rises with less twist than foreseen. The absolute values differ from those recorded by the elder sibling. The pressure of the heliosheath seems different. The thickness of the sheath along each path is not the same, and the density beyond shows spatial structure. Together, the two crossings reveal a frontier that is neither spherical nor steady, but mottled by solar cycle waves and by the local interstellar medium's patchwork of pressure and field. What makes the heliopause singular is the sudden swap in how particles move and in how energy flows. Inside plasma is dominated by the sun's field and by outflowing ions that carry spiral patterns impressed by the star's rotation. Outside the interstellar field and plasma carry their own long memory set by distant sources and by the quiet churn of turbulence on scales larger than planetary orbits. At the boundary, neutral atoms from outside charge exchange with solar ions and create energetic neutral atoms that fly back inward in straight lines, a backscattered whisper that images near Earth turned into the famous ribbon that first suggested the draping geometry. At the boundary, magnetic reconnection may stitch and unstitch field lines, allowing pockets where solar plasma and interstellar plasma mingle. The Voyagers do not see every stitch, but their counts and tones indicate that the seam is not a simple weld. The cosmic ray surge is more than a curiosity. It calibrates the shielding that the heliosphere lends to every organism and instrument under its roof. As the craft step outside, they report the raw spectrum of particles that the galaxy offers. Inside those spectra are softened by modulation that waxes and wanes with the solar cycle. The difference between inside and outside is the measure of the heliosphere's protective reach. For future journeys, the dose and energy of particles beyond the door set the demands on shielding and the endurance of electronics. The surprise that the field direction rotates less than expected across the boundary suggests that the heliospheric nose may be magnetically pinned to the local field, easing the change in direction across a sheath that is thinner in orientation than in strength. This complicates simple pictures, but helps refine designs for plasma sails or magnetoshells that might one day try to couple to the medium. The density values inferred from plasma waves after the Voyager 1 crossing and measured directly by Voyager 2 place the craft in a region of the local bubble, where the electron number is low, by earthly standards yet higher than that of the Helios heath. The interstellar plasma is cool, steady and threaded by a field of a few microgauss in human terms, which becomes simply a few millionths of the strength of a refrigerator magnet in everyday speech. Even so, over astronomical distances, such a field shapes the paths of cosmic rays and guides currents that can store and release energy in reconnection flashes. The heliopause sits as a contact discontinuity between two regimes of magnetic control. The solar wind presses outward, the interstellar medium presses inward, and between them a thin layer carries the currents that balance the books. When pressure waves from solar outbursts arrive years later, they make that layer ring, and the voyagers hear the bell. The crossings sharpen navigation ideas. If a craft aims to leave quickly, it should plan for the varied thickness of the heliosheath, and for the fact that the heliopause's distance will shift with solar phase and with direction relative to the interstellar inflow. The upwind nose may be closer than the flanks. The downwind tail may stretch for hundreds of astronomical units. A beamed sail might wish to angle for a quadrant where the sheath thins. A fusion craft less concerned with a few tens of astronomical units may still care deeply about the turbulence that can shake a magnetic nozzle, or about the reconnection that could sap plasma thrust. The precise places where cosmic rays surge most, and where the field lines drape most tightly, become part of departure charts. The psychological power of the crossings cannot be ignored. For decades the phrase interstellar space lived in textbooks and in dreams. When the instruments recorded the swap, the words acquired weight. The heliopause is not the solar system's ultimate edge because the distant Oort cloud extends the family's influence for light years, but in plasma terms this is the first true outside. The instruments do not shout. They tally counts, draw lines and hum with wave tones. The drama is in the accumulation. Solar particles down, galactic particles up, field stronger, density higher. Tone of plasma waves shifted. The quiet insistence of the data makes the case. The door is thin, but it is felt. The intrigue remains because each neat signature carries roughness. Voyager 1 reported a boundary with the density higher than simple models of the local bubble, suggested perhaps because the heliosphere's motion and its interaction with the interstellar field compress a sheath of plasma on the outside. Voyager 2, crossing in another place and at another solar phase, found a different gradient. The hydrogen wall detected in glow by other instruments may be part of this story, a compressed region upstream of the nose that thickens with solar wind pressure changes. The door is a curtain that puffs and sags, not a frame set in stone. Future interstellar precursor missions aim to measure the structure in 3 dimensions, By sending multiple probes along different bearings, each with better plasma instruments and clocks, synchronized to read faint responses to orchestrated signals. For now, the 2 lines traced by the voyagers are precious because they show that leaving in the plasma sense is possible with craft built in an earlier era, and because they outline the questions that remain. How does the draped field twist around the tail? How do reconnection events stitch holes in the sheath? How thick is the hydrogen compression ahead of the nose? How do solar cycles and perhaps longer solar variations breathe through the boundary to pump waves into the local bubble? Each answer will refine the tactics of departure. The heliopause crossing is not the final proof that we can leave, but it is the first firm touch of the outside, a handshake with the medium that fills the space between stars. The hydrogen wall is a name given to something that does not stand still. Ahead of the heliopause, where the solar wind meets the interstellar medium, there appears to be a swelling of neutral hydrogen, a slow thickening, shaped by charge exchange with outflowing ions, and by the press of the magnetic field that wraps around the solar domain. It is not a masonry edge, but a river bar formed where currents meet and grains accumulate, and its presence is traced not by sight alone, but by delicate signatures that accumulate across missions and decades. Ultraviolet spectrographs looking at nearby stars see a telltale absorption in the hydrogen line that is stronger than can be explained by the interstellar medium alone. The extra dip suggests a local surplus of atoms along the line of sight, a cushion formed as the storm of solar particles slows outside and neutral atoms linger. At other times, spacecraft within the solar system register a glow of scattered ultraviolet light from hydrogen that is brighter upwind than downwind, as if a headwind had compressed a sheen ahead of the nose. The interstellar boundary explorer imaging neutral atoms born at the frontier draws a broad ribbon across the sky that seems to align with the draped external magnetic field, and in that alignment some researchers see the focusing of interactions that would help raise a wall. Later, as the voyagers move outward, one craft hears plasma waves whose tones indicate a density beyond the heliopause higher than expected, consistent with a compression of electrons outside the sheath. Another measures a direct jump in density at the crossing again, implying that the space just beyond the boundary is not thin but slightly crowded. These threads point to a simple picture. The outward push of the solar wind creates a cavity. The interstellar medium pushes back. Neutral atoms indifferent to magnetic lines until they are ionized drift in slow as they meet a counterflow and pile up into a gentle mound. Yet the picture refuses to stay simple. When one mission tallies the ultraviolet glow, the brightness waxes and wanes with the solar cycle, in ways that suggest the wall grows taut during strong solar output and relaxes during quiet years. When a distant imager looks again, the pattern shifts, hinting that the shape of the wall depends not only on solar mood, but also on the direction and strength of the interstellar magnetic field and the density of the local cloud. Some models place more emphasis on charge exchange, building a wall from a dance of electrons that turns fast solar ions into fast neutral atoms that fly back inward, while leaving slower neutrals to accumulate outside. Other models emphasize magnetic draping in which the external field lines bend around the heliosphere and squeeze the plasma and neutrals into a lens-shaped bulge. The truth may combine these mechanisms and change its balance with time and with direction. The debate gains weight because similar signatures appear around other stars. The Hubble Space Telescope has seen extra hydrogen absorption towards several nearby systems interpreted as the outer skins of astrospheres, the star-carved bubbles where other stellar winds meet their own interstellar surroundings. If other stars build hydrogen walls, our Sun likely does too, but the thickness, density, and texture may vary with stellar age wind power and the patchiness of the local medium. In our case, the local interstellar cloud through which the Sun moves appears warm and partly ionized, with a magnetic field that sets a preferred direction. Where that field meets the solar wind head on the compression ought to be strongest. Yet the asymmetries seen by Interstellar Boundary Explorer and the differing heliopause distances sensed by the two voyagers imply that the wall is lopsided with folds, bright knots, and thin places that can move as the solar cycle breathes. A puzzle rises in the numbers. Some reported densities just outside the heliopause are higher than textbooks once suggested for the local bubble. Either the bubble's plasma is more structured than a smooth average, or the heliosphere's motion and magnetic draping create a local enhancement that a distant average would miss. The wall may thus be a local product of motion through a non-uniform sea, awake in a bow wave joined, thickened where field lines converge and thinned where they slip. The intrigue deepens when one considers how the wall would look to a fast precursor probe. Approaching upwind, a craft might see a gradual increase in neutral hydrogen and a rise in electron density before the more abrupt changes at the heliopause. Approaching along the flanks, the wall might appear thinner and more irregular. Downwind, it could vanish into a tail where neutrals and ions commingle over long distances. Measurements along different bearings would map the bulge in 3 dimensions and resolve whether the hydrogen wall behaves as a smooth bow or as a string of ridges aligned with the external field. For the project of leaving the wall is not only a scientific curiosity. A beamed sail racing outward on a path that crosses a denser region of neutrals will experience more charge exchange at its leading edge, altering the distribution of electric charge across the sail and perhaps coupling to the magnetic field in ways that could twist its orientation over long coasts. A fusion-driven craft that expels charged exhaust might find that a denser external plasma reflects some of that exhaust back, shaping a subtle pressure term on the nozzle. For a habitat crossing in slow time, the wall's density sets a baseline for the flux of energetic neutral atoms that can enter unimpeded, which in turn sets part of the radiation environment. The hydrogen wall also reframes the meaning of the first step into interstellar space. The heliopause in plasma terms marks a crisp swap in control, but the hydrogen wall makes that swap feel thicker. The first taste of the outside may come not at the boundary, but before it, in a rise of neutral density and in the behavior of particles that respond to that rise. This layered exit suggests a new class of measurements for future scouts. One could imagine small probes released along several bearings to count neutrals, listen to plasma waves, and watch how the external field bends. Each would cross the wall at a different place, and their combined lines would sketch the fold of the sheath. Some could carry tiny ultraviolet spectrometers to look back toward bright stars and measure the extra absorption from within the wall itself, turning the sky into a backdrop chart. The hydrogen wall motivates a final question that runs deeper than naming a bulge. Boundaries that breathe make timetables waver. If the wall thickens during a long solar maximum, or during a passage into a slightly denser interstellar patch, then the effective thickness of the frontier changes, and the moment when instruments register interstellar conditions shifts outward. A mission that plans to announce a crossing at a certain distance may need to accept a band of possibility instead of a single number. The suspense is quiet but real. The difference between a slightly compressed wall and a relaxed one could be many astronomical units, a margin that on human timescales equals years of flight. The great advantage is that the wall reveals itself from within months and years before a craft arrives, through changes in ultraviolet glow and in the sky-wide maps of neutral atoms that respond to the drape of the external field. With patience, these clues can turn into forecasts that advise when and where to go for a cleaner or a more challenging passage. The hydrogen wall therefore stands as both sign and teacher. It marks the place where our outgoing breath meets the breeze of the galaxy, and forms a tide line of atoms that briefly belong to neither side. It teaches that leaving the solar system is not a moment but a passage through textures made by motion, magnetism and exchange. It invites missions to read the thin handwriting in ultraviolet light and in particle counts, and to plan departures that respect the idea that the edge can swell and thin like a living shoreline. In this view, the question of whether we will ever leave turns on how well we learn to read that shoreline. The wall is not an obstacle built to stop us. It is a contour that tells us where the forces are strongest and where the seam is stitched tight or loose. To cross with grace is to know that seam in detail, to expect its changes, and to let the mystery of its folds sharpen the will to measure more finely. The edge of the solar system is threaded with magnetism that does not hold still a weave of lines and knots that twist, merge and unravel, as if a loom were being worked by several hands at once. Magnetic fields are not material in the way dust is, but they give charged particles rules to follow, and those rules change as the field bends. Near the sun, the rotating star winds its magnetism into a spiral that rides outward with the solar wind. Farther away, that pattern falters as the wind slows and pushes against the interstellar medium. The plasma there, a thin gas of charged particles, obeys the mathematics of magnetohydrodynamics, a framework that treats the field and the flow as linked. In that framework, turbulence emerges almost inevitably. Large ripples break into smaller waves, and energy cascades down the scales until the smallest gyrations warm the particles. The voyagers have crossed into a realm where this cascade runs both sides of the heliopause, and their instruments hear it in the way the magnetic field wanders, and in the songs of plasma waves that change tone with density and with speed. In the heliosheath before the crossing, the sun's field flattens into sectors separated by current sheets, thin layers where the field flips direction. These sheets can wrinkle and roll, sometimes tearing and reconnecting in events that briefly change topology and release stored magnetic energy as heat and as accelerated particles. Such reconnection does not need a single flare. It can happen along folded surfaces that drift like seaweed. The effect on the flow is subtle, but deep. Field lines that once trapped low-energy charge particles can open, allowing them to escape. Other lines can close, trapping new populations. As these events pepper the heliosheath, the region becomes a quilt of domains with slightly different history. When a wave of pressure from a solar outburst crosses this quilt, it compresses some domains more than others, creating gradients that later relax into turbulence. The Interstellar Boundary Explorer, which images energetic neutral atoms created by charge exchange at the frontier, revealed a ribbon that traces where the external magnetic field likely aligns with the viewing direction. The brightness and persistence of that arc suggest that the draping of the interstellar field around the heliosphere is not smooth. There are likely wrinkles where field lines bunch up and valleys where they spread. Those shapes govern where reconnection most often stitches and unstitches the seam between inside and outside. Voyager 1 and Voyager 2 separated by many astronomical units, and by different crossing points. Both record magnetic fields that strengthen beyond the heliopause, but do not whirl in direction as sharply as early models expected. This hints that the draped interstellar field may run nearly parallel to the heliospheric boundary. In the regions they sampled a configuration that could suppress some kinds of turbulence while favouring others. Where field lines run parallel to the boundary, reconnection may be patchy, occurring in intermittent islands, rather than in a continuous sheet producing a speckled pattern of entry points through which particles can mix. Magnetic turbulence influences the transport of cosmic rays, the high-energy messengers from distant supernova shocks and from other violent sources. Inside the heliosphere, spiral field lines and solar cycle changes modulate their paths, raising and lowering the flux at Earth over years. Outside the interstellar field and its own turbulence bend those paths on much larger scales. Near the heliopause, the spectra that the voyagers read show how the transition sorts particles by energy and by pitch, angle the orientation of their motion around the field. If turbulence is strong on certain scales, it scatters those angles and makes the distribution more isotropic. If the turbulence is weaker, the distribution retains memory of preferred directions. The counts show both conditions at different times, an observation that argues for a boundary that shifts personality as solar-driven waves arrive and as local reconnection events occur. None of this is idle structure. For any craft that tries to couple to the medium magnetism is a handle, a plasma sail that generates its own magnetic bubble to deflect ions, a magneto-shell that inflates a field to break against a planetary atmosphere, a magnetic nozzle for a fusion-driven engine, all must operate within the ambient field. If the field drapes strongly and lines are taut, the coupling may be efficient. If the field is patchy and turbulent, the interaction may fluctuate, causing thrust or drag to wander. For a thin-beamed sail, even a weak charge that builds on its surface as neutral atoms are ionized at the leading edge can make it feel the field twisting it subtly over long times. In a human habitat coasting for decades, equipment designed to bleed off accumulated charge must handle environments where the magnetic direction and turbulence amplitude vary, or else the habitat may experience persistent torques that complicate attitude control and communication pointing. Turbulence also affects dust. Grain-sized particles that become charged by sunlight and by collisions begin to dance to magnetic tunes. Their paths can kink, their residence times in certain regions can change, and their impacts on detector plates can become more or less frequent depending on the balance between flow speed and field fluctuations. The record of dust counts from missions in the outer solar system shows variations that likely reflect not only the sources of the grains, but also the changing fields they have to cross. In the inner heliosphere, the Parker Solar Probe has found that magnetic lines can flip in sharp kinks called switchbacks, unexpected signatures of energy released near the Sun that complicate the origin story of the solar wind. While those switchbacks are a near-Sun story, they teach that the field can store surprises even where models once expected smoothness. By the time the wind reaches the outer realms, the memory of those inner switches may be softened but not erased. The turbulence in the heliosheath thus carries echoes from the star as well as impressions from the galaxy. The cascade of energy through scales is not purely of one birth. It is a mixed ancestry that a careful probe could disentangle by measuring fluctuations over a wide range of frequencies and sizes. Such measurements are not trivial. A single craft samples turbulence as a time series along its path, translating temporal changes into spatial structure by assuming that the flow sweeps patterns past like a conveyor belt. This assumption, called the frozen flow hypothesis, has limits in regions where the flow itself changes speed or direction. A chorus of small probes synchronized and spread across the sheath could therefore do better. They could read the same wave crest at different points, measure phase speeds and map reconnection islands in 3 dimensions. Between the voyagers there is already a hint of such a network, but future designs could make it deliberate. Magnets and turbulence also shape how the heliosphere itself looks to the outside. To a traveller approaching the Sun, the draped field and the local turbulence would decide how far energetic particles can enter before turning back, shaping a halo of emission that telescopes might one day resolve around nearby stars. By comparing these halos for many systems, astronomers could infer the vigor of stellar winds and the texture of local interstellar fields, placing our own heliosphere in a larger family. Within that family there would be young stars with fierce winds and thick turbulent sheaths, and older stars with softer winds and thinner drapes. The sun would sit somewhere in the middle, its boundary neither the taut drumhead of a hot star nor the fragile skin of a dying one. What all of this means for leaving is that there is no clear water beyond the reef, only a new sea with different rules. Magnetic threads can guide or hinder. Turbulence can wade the currents into eddies that a craft may surf or that may buffet it. Reconnection can open sudden doors between inside and outside that were shut a moment before. It is possible that there are preferred lanes where the field is smoother, where the ribbon-like alignment seen by the energetic neutral atom imager marks corridors of relative calm. It is equally possible that the best path changes with the solar cycle, that the quietest window appears when the sun is either most active or most subdued. The edge teaches patience. A mission must be built with margins that accept a frontier where the velocity of the wind, the strength and angle of the field, and the amplitude of the turbulence drift over spans of years. The reward for such patience is not only safe passage, but also a map that future travellers can use a chart of magnetic shoals and gentle runs drawn in the universal language of field strength, density and wave tone. In that chart, the mystery remains as an invitation, because magnetism is notoriously rich. It stores energy silently and releases it without warning. It couples microscopic gyres to macroscopic drapes. It is the invisible architecture that a departing craft must learn to feel. If departure is a question, then the answer flows through these threads. Measure them, respect them, and let their turbulence become part of the plan rather than a surprise at the door. The outermost architecture of the solar system stretches so far that the word edge begins to lose meaning. Beyond the giant planets and the band of icy worlds that circle in the Kuiper belt lies a diffuse sphere of comets that extends for light years, a slow fog named the Oort cloud. It is a population more inferred than seen, because its members spend almost all of their time in deep darkness, moving at walking speeds over vast arcs, their orbits stretched into long ellipses by ancient kicks. When one of these bodies falls sunward, it becomes a long-period comet, a messenger, whose chemistry and motion declare a source far beyond the disciplined lanes of the planets. If leaving the solar system is defined by the last influence of the sun, then the Oort cloud complicates the story because the sun's reach in gravity and memory is written into these distant reservoirs. The path outward must cross a region where the family still lingers even as the galaxy begins to speak more loudly. The cloud is thought to come in two parts. The inner portion, sometimes called the Hills cloud, is a thick shell beginning beyond a few thousand astronomical units and extending to perhaps a few tens of thousands. The outer portion swells from there to distances where the sun's pull competes with the faint tug of the Milky Way, a limit often called the Hill sphere in dynamic context. The inner shell is likely denser, a storehouse of bodies that did not quite escape when the giant planets rearranged the early system. The outer shell is sparser, a diaspora of ice-packed fragments kicked outward by close passes with growing planets and then rounded into a sphere by the gentle hand of galactic tides and by distant star flybys. It is a museum of beginnings placed in the attic of space. Within that museum lie clues. The chemical fingerprints of long-period comets show high fractions of volatile ices, complex organics and trapped gases that condense at low temperatures, suggesting birth in the cold outskirts of the protoplanetary disk. Some comets carry grains that appear to have formed at higher temperatures near the newborn sun, and then were transported outward before being locked into icy matrices. This mixing tells of early turbulence and exchange within the Sun's natal disk. Later, as the giant planets migrated and scattered planetesimals, many fragments were flung on paths that grazed escape. Galactic tides and the passing of sibling stars in the Sun's birth cluster softened those aphelia turning stretched ellipses into more rounded orbits spread across many inclinations. In this picture, the Oort cloud becomes both relic and record, a three-dimensional diary of youth, written on bodies that sleep for millions of years between brief flashes near the Sun. Dynamics in this realm whisper rather than shout. The direct gravity of the planets drops with distance, but at tens of thousands of astronomical units, the slow tide of the galaxy becomes comparable. That tide is not a wave of water, but the collective gradient of many distant masses, a field that can nudge the distant comet's perihelia inward over long cycles. Close passages of stars add sharper notes. A red dwarf passing within a light year can stir a faint shower, sending a few more objects sunward over the next million years. The rare, very close pass can send a stronger surge. Geological layers on Earth hint at episodes of enhanced comet influx, but the evidence is debated, and the patterns are likely smeared by erosion and by other cycles. Regardless, dynamical models show that the Oort cloud is a living halo continually perturbed, slowly eroded and slowly replenished by the diffusion of bodies from the inner to the outer shell. The mystery in these calculations deepens with objects like Sedna and other detached worlds whose perihelia sit too far from Neptune to be easily explained by current planetary gravity alone. They hint at past encounters, perhaps with a sibling star in the Sun's birth cluster, perhaps with a transient planet that has since gone, or with a still undetected massive body in the far reaches, an idea that some researchers have framed as a hypothetical ninth planet. Evidence remains circumstantial, but the orbits of a subset of distant trans-Neptunian objects seem clustered in directions that invite new gravity. The intrigue is not in claiming a discovery before it is earned, but in recognizing that the outer architecture bears scars and signatures of events beyond the familiar. For a leaving craft, this halo raises two practical questions. First, how long does the word leaving remain honest if the Sun's family extends for light years? Second, what hazards or resources does this expanse present? The first answer is sobering. A probe that crosses the heliopause and sails on at tens of kilometers per second will need many thousands of years to pass through the outer shell if it flies directly outward. The voyagers, despite being in interstellar plasma, will still be within the statistical bounds of the Oort cloud for a span longer than the history of writing. In this sense, leaving is not a clean break but a long farewell. The second answer is two-faced. The cloud is not dense. The neighbourhood of any random path is likely empty by human standards. Yet the numbers are large enough that over light-year scales the chance of interaction rises. For a slow habitat, micrometeoroid shielding must assume occasional dust and rare small bodies on poorly known orbits. For a fast sail, even tiny grains can erode surfaces over decades, and the strategies for charge control and for self-healing coatings gain weight. The cloud also offers thought for future harvesting. In a far future where propulsion and patience align icy bodies in the inner shell, could be oases, sources of water, volatiles and radiation shielding strung like dim beads in a sparse necklace along the path outward. Such a network would not be a highway, but a set of waypoints for a civilization that thinks in millennia. The Oort cloud further blurs the boundary between local and interstellar because it interacts with the galaxy. Interstellar comets that wander from other systems may thread the outer shell on their way through. A few have been seen on hyperbolic paths in recent years, their speeds at infinity too large to belong to the Sun. Their arrival proves that the Oort clouds of many stars are not hermetic. Bodies drift between systems in a slow trade mediated by galactic tides. This slow exchange means that the chemical and dynamical record in our cloud includes a faint dusting of visitors, and that our own debris may one day pass near another star and shed molecules into a different sky. In contemplating departure, the scale of the cloud challenges engines and definitions. Fusion propulsion that could maintain accelerations for months might cross the inner shell on timescales that fit within a human life, but the outer shell remains measured in lifetimes of a culture rather than a crew. Beamed sails that reach a few % of the speed of light could leave the cloud within centuries fast by cosmic standards, still long by personal ones. The choice of trajectory matters. A path that dives inward first to perform an orbith burn near the Sun could gain enough speed to shorten the crossing, while a straight outward climb from the planets crawls by comparison. Yet even the fastest path remains a thread through a volume where the Sun's influence fades slowly rather than stops. The quiet wonder here is that the Oort cloud embodies the solar system's memory of its making and of its neighbours. It is the echo of giant planet formation, the imprint of early cluster days, the stamp of galactic tides, and perhaps the fingerprint of unseen masses. To pass through it is to pass through a museum that rarely opens its cases. Each long-period comet that brightens in the inner sky is a signboard from that museum, offering a page from a book that mostly stays closed. Instruments on craft like New Horizons and telescopes on Earth and in space have begun to read these pages more carefully, but the full text remains beyond current reach. Future surveys with deeper reach will find more distant detached bodies and will map their angles with respect to the Sun and the plane of the planets, refining the story of the outer architecture. Small precursors that fly to hundreds of astronomical units could read the dust and neutral gas environment in situ, tasting the fringe of the inner shell, and in doing so give the first local notes from a region otherwise known only by comets that rush by and leave. In the guiding question, the Oort cloud does not forbid departure, it changes its meaning. One can step into interstellar plasma while still being surrounded by family heirlooms. One can measure galactic fields while still under the gentle claim of the Sun's ledger. Leaving becomes less a gate than a long path through a home whose walls have grown thin and porous. The mystery that follows is whether the definition of departure should be the end of plasma control, the end of cometary influence, the end of gravitational claim, or simply the end of caring which of those applies. For now it remains a gradient, and in gradients there is room for both science and wonder. The idea of using gravity to leave the solar system seems paradoxical, yet it is one of the few ways nature offers to trade distance for speed without paying a price in fuel. Gravity assists are not slings in the literal sense, but exchanges of momentum between a small traveller and a massive planet that barely notices the transaction. When a craft approaches a planet from behind relative to the planet's motion around the Sun, it falls into the planet's gravity well and leaves with a boost because it has drawn a fraction of the planet's orbital energy. The gain is tiny for the planet but vast for the probe. When a craft approaches from ahead, it can be slowed, instead giving some of its energy to the planet. The mathematics is simple, but the choreography is delicate, requiring precision in timing, angle, and altitude. The path must thread the planet's gravitational sphere of influence at just the right depth to bend the trajectory without plunging into an atmosphere or colliding with moons. The reward is measured in kilometers per second, each increment earned by planetary motion rather than by propellant. The concept reaches beyond planetary flybys to the deeper principle called the Oberth effect. A burn executed while moving rapidly within a gravity well yields a larger increase in total energy than the same burn done far away, because kinetic energy grows with the square of velocity. Firing an engine near a planet's periapsis, or especially near the Sun, multiplies the effect of the same thrust. A dive close to the Sun, if a heat-resistant craft can survive it, could therefore amplify a limited supply of fuel into a powerful departure. The equations turn into imagination. A probe falls sunward, gathers speed until it races at hundreds of kilometers per second near perihelion, and fires a short engine pulse that converts much of that speed into escape energy. Once past the fire, it glides outward at a pace that otherwise would have required impossible thrust. The practical obstacles are immense. Heat rises exponentially with proximity. The radiation and particle environment near the Sun can shred electronics and weaken materials. Yet the idea persists because the payoff is huge. Designs for interstellar precursors often include such a solar obverth maneuver, using advanced heat shields and automated timing to perform the burn at the precise moment of deepest approach. Gravity and motion thus become allies rather than prisons. The interplay between planetary and solar assist can be imagined as a ladder. Each planet provides a rung, and the Sun itself is the last and deepest. A craft might first steal from Earth and Jupiter, diving inward, then from the Sun itself climbing outward on the rebound. Simulations show that by weaving through multiple assists, a probe launched with current rocket technology could achieve speeds several times greater than the Voyagers, reaching hundreds of astronomical units within a human lifetime. A more daring plan uses a giant planet to send a craft toward the Sun, a close solar swing for an obverth burn, and then a final outward trajectory. In this scheme, the planet does not only give speed, it also gives geometry, turning the craft onto a path that makes the solar dive possible. The language of slingshots and dives hides subtle constraints. Every assist changes not just speed but direction, and each change must be planned so that the next encounter is possible. The solar system is a dynamic puzzle of moving targets, and mission planners must pick windows that may open only once in decades. The alignment that made the Voyager Grand Tour possible will not return for more than a century, yet other opportunities arise with different goals, a sequence for leaving in one direction, another for exploring the outer flanks, still another for intersecting the solar apex where the Sun moves through the local interstellar medium. Future missions may choose paths that exit upwind or downwind, depending on the questions they want to ask about the heliopause and beyond. The subtlety of gravity assists also reshapes thinking about propulsion. Instead of brute force burns, missions can rely on a series of encounters that use celestial bodies as engines. This principle extends to the idea of using the gravitational field of the Sun itself in a sustained way, not just for an obverth impulse, but for long arcs guided by relativity. Some have proposed gravitational assists not only within the solar system, but with stars themselves. In distant futures, a civilization could use stellar flybys as interstellar braking or acceleration methods, chaining suns as if they were giant waypoints in a galactic railway. That vision reaches far, but the mathematics begins here with a craft looping behind Jupiter or diving toward the Sun to grasp a few extra kilometers per second. The intrigue of gravitational assists lies also in their asymmetry. The energy gain depends on the planet's orbital speed and on the angle of approach. Jupiter offers more than Earth. Neptune offers less. The Sun, with its immense pull, offers the greatest potential if one dares to descend. Each assist has a cost in navigation and in radiation exposure because the craft must pass through strong fields and sometimes within belts of charged particles. Each has a payoff in speed and in scientific return, since the path near a planet opens the door to observations. The voyagers proved that planetary science and deep space mechanics can serve one another. The encounters that bent their paths also delivered images that changed understanding of the outer planets. For leaving the solar system in earnest, the same philosophy applies. The road outward can double as a survey of gravitational landscapes. The interplay between gravity and motion even reaches into more speculative domains. In relativity, massive bodies bend space-time, and a trajectory through such curvature can in principle be optimized beyond Newtonian intuition. Small corrections for time dilation and frame dragging near rotating bodies like Jupiter or the Sun become measurable over decades, and precision navigation can exploit or must correct for them. The future of deep navigation may thus require not only celestial mechanics, but relativistic mechanics, a seamless dance between geometry and gravity. Engineers planning interstellar precursors must think not only about propulsion, but also about trajectory art, the use of the solar system itself as part of the engine. A well-timed sequence of assists can triple the reach of a mission without adding a single kilogram of propellant. A close solar pass can convert a small burn into an enormous gain. The concept of to leave by falling is counterintuitive yet beautiful, a reversal of instinct that turns gravity from obstacle to partner. It is also a metaphor for patience. Gravity assists demand, waiting for alignments, calculating years ahead, accepting that the most direct path may be slower than the elegant one. They represent an intelligence that listens to the music of orbits and finds rhythm instead of resistance. In that rhythm, even small craft can achieve what raw power cannot. The solar system becomes not a cage, but a resonant instrument that, if played with skill, can send notes into interstellar space. The next steps in this practice may come from missions that blend chemical, electric, and gravitational thrust. Ion engines could adjust timing between planetary encounters, allowing finer choreography. Solar sails could alter inclination over decades, setting up dives that lead to faster exits. Each of these approaches extends the philosophy that leaving is not a single push, but a continuous dialogue with celestial motion. The same mathematics that guides a satellite around Earth now guides probes to the stars. What remains uncertain is how far such methods can take us before the faint pull of the planets fades into the open tide of the galaxy. Perhaps there will always be another well to borrow from, another field to surf. Perhaps the true art of departure will always lie in knowing when to fall inward, so that one can leave outward, riding gravity's embrace until it turns into release. Fusion sits at the center of dreams to leave because it promises to turn a pinch of common matter into long rivers of thrust, and because it has already lit the stars that mark our destination. In a fusion engine, the goal is not to build a miniature sun, but to tame brief contained bursts in which light nuclei join release energy and fling charged particles rearward as a directed wind. Two paths dominate the sketches. One gathers a hot plasma in magnetic loops and squeezes it long enough that deuterium and tritium, or deuterium and helium-3, collide and fuse their charged products, channeled by a magnetic nozzle into a jet. The other compresses tiny fuel pellets so quickly and violently that they ignite each micro-explosion, becoming a pulse of plasma that hammers against coils and fields, a rhythm of detonations that averages to a steady push. In both cases, the engine lives by fields and timing. The vessel becomes a cathedral of magnets and radiators, a place where materials must stand against heat radiation, and a drumbeat of stress for years. When engineers write numbers on paper, the allure is stark. The energy density of fusion rivals that of the deepest chemistry by many orders of magnitude. A ship that carries deuterium in tanks the size of houses could in principle push for months without refill. A deuterium and tritium reaction yields a fast helium nucleus and a faster neutron. The helium nucleus is charged and bendable by fields usefully part of thrust, while the neutron slips through and turns its energy into heat inside the structure, a penalty that forces thick shielding and massive radiators. A deuterium and helium-3 reaction steers more energy into charged products and fewer neutrons friendlier to hardware and to crew, but helium-3 on Earth is rare and costly, and gathering it from the atmospheres of giant planets would demand descents into deep gravity wells and heroic engineering to lift it out. Some designs imagine breeding tritium from lithium and then letting tritium decay into helium-3 in warehouses that keep time with patient calendars. Between the pure options lie hybrid schemes where magnetic fields trap some of the neutrons, or where exotic catalysts nudge reactions to favour charged products. The core challenge is to shape exhaust that is fast collimated and continuous enough to turn months of power into a single bright arc in velocity space. Magnetic nozzles promise such shaping. In them a torus of fields wrangles the newborn plasma, letting charged particles spiral along lines that flare into a directed jet, because the particles already carry energies measured in millions of electron volts, and because their velocities reach a few % of the speed of light in everyday phrasing, the effective exhaust speeds can be many thousands of kilometers per second. That is the central magic. Even at very low thrust, such exhaust speeds let a craft add up gentle pushes into tremendous changes in trajectory. A ship that starts heavy near the sun can slowly trade fuel for speed, the slow arithmetic of propellant becoming a final few % of light speed after a season of patience. The difficulty is that the very processes that grant speed also inflict damage. Neutrons in brittle metals stir defects in crystals and make things whisper radioactivity that disturbs electronics and biology. Alphas and protons wear at the nozzle walls. Fields that were meant to be guides buckle if a magnet quenches. The structure must soak up waste heat, steadily radiating it away over surfaces that may span football fields shining in dull red and deeper colours into space for as long as the engine hums. The radiators themselves must be protected from sputtering by backflow and from micrometeoroids, and they must be arranged in wings or spines that do not shadow the nozzle or the antennas. Every kilogram added to shielding and heat rejection is a kilogram that does not become speed, and so the design is a negotiation between physics and logistics conducted under the stern judge of mass. Pulse concepts carry a different beauty and a different risk. In a pulsed microfusion engine, pellets of frozen deuterium mixtures are injected into a chamber and crushed by lasers, by heavy ion beams, or by magnetic implosions that turn the surface into a rushing piston. Each pellet detonates into plasma, whose roar is caught by fields and angled rearward. Thousands of times per minute the engine must breathe in a new pellet, crush it to fusion conditions, and swallow the shock of the blast without tearing itself apart. The rate must be high because each pellet contains only a small amount of fuel. Smoothness emerges from the blur of many controlled detonations. The echo of an older idea rings here, the concept of pushing on a pusher plate, with nuclear pulses first penned in a century that tolerated such bravado. In updated visions, the plates are replaced by magnetic mirrors that feel the pressure of charged plasma without the wear of direct contact. The scale remains daunting. Precision pellet fabrication by the millions targeting systems that never misplace a shot chambers that clear debris and recover in microseconds. All of it must function across years, yet the reward would be a ship that steps outward on a drumbeat, its glow rhythmic and its acceleration gentle enough to be kind to the crew, while relentless enough to build to unheard speeds. Between the continuous and the pulsed sit-magnetized target fusion concepts that try to use magnetic fields to pre-order the plasma and then crush it quickly, capturing some advantages of both worlds. A field reverse configuration might confine a torus of plasma just long enough that a sudden compressive ring sends conditions through the threshold, where fusion ignites and yields a more tractable spectrum of charged exhaust. The exhaust then unfurls along lines engineered to give it a gentle swirl and a tight cone. These engines would be neither steady torches nor drumbeat cannons, but breathing hearts, whose cycles align with vibrational limits in their frames. Material science becomes destiny in all cases. High-temperature superconductors promise stronger fields at lighter mass, yet they are delicate to radiation and to mechanical shock. Ceramic composites resist heat but can be brittle. Metals carry heat well, but soften when bombarded by fast particles or when held at high temperature for years. Some plans place the engine at the end of a long boom, with the habitat far ahead, a shadow shield of dense material between them, so that neutrons and stray ions fall on sacrificial plates, while crew quarters dwell in the wake. Other plans separate the engine entirely, pushing unmanned cargoes at higher power and letting crewed vessels travel slower under less hostile regimes. Across all variants, the same arithmetic returns. How much specific power can the engine deliver for how long? How much of that power ends up as heat that must be rejected? How thick must the radiation protection be? And how well can the vehicle shape its exhaust into momentum that points exactly where it is needed? The arithmetic ties back to navigation, because a fusion ship could marry engine and trajectory art. It could choose to coast most of the time and save pulses or burns for a deep solar dive, performing an Oberth maneuver that multiplies its power. It could also remain perfectly steady for months, climbing a smooth exponential in speed that ends with a braiding of stars in the forward view and a red shift in the voices from home. Timelines enter soberly. To build such engines requires progress in fusion confinement that has so far in power plants come slowly. Yet the constraints for propulsion are different. An engine need not hold a plasma forever. It needs only to extract a portion of energy and direct it. A reactor demands continuous stability to feed a grid. A rocket can be noisy and even wasteful if the fraction it harnesses becomes thrust. This distinction keeps the door open for propulsion designs to succeed before commercial fusion lighting cities becomes common. Even then, the practicalities of crewed travel demand more than engines. A habitat must recycle air and water for years. It must carry stored food or grow it under light that prints day and night on demand. It must shelter minds from isolation and bodies from radiation. Fusion solves the energy shortage but not the human one, and so the architecture of a leaving mission braided from fusion would still look like a small world with its own climate, its own rituals of maintenance, its own magnetosphere in miniature generated to deflect stray ions. The mystery that fusion brings is choice. Which reaction to favour, which spectrum of particles to trust, which balance between speed and survivability to strike. Deuterium and tritium push harder but punish hardware. Deuterium and helium-3 run cooler on neutrons but demand a difficult supply chain. Pulses promise compact engines but require exact choreography beyond current industrial rhythm. Continuous fields promise elegance but hinge on magnets that hold at strengths and temperatures not yet routine. The promise is large enough that many paths remain worth walking. Each laboratory that tames a burst for a few microseconds, each magnet that holds a hotter plasma for a few minutes more is a step on a staircase that could lead to real ships. The question of whether we'll ever leave thus takes on a new flavour. With fusion, the distance to be crossed becomes a manageable calculation. while the unknowns shrink to engineering patience and the will to accept that the first engines will be crude cousins of future elegance. The first fusion ships may cough and glow and run at fractions of their theoretical limits, yet even those fractions could carry scouts to hundreds of astronomical units in a few decades and onward to the thin plain between the stars. In the quiet hum of such a ship, the sound of charged particles turning into motion would be a hymn to methods learned from the sun repurposed into a path away from it. Light itself can push, and a sail can ride that push, if it is bright enough, broad enough, and held to a steady aim long enough that the momentum of countless photons adds into speed. In the simplest view, a beamed sail is a mirror, and a beam is a river. But the true design is subtler, because a sail that merely reflects must also shed heat, must not twist under uneven pressure, and must remain centered in a stream that can wander as it crosses air or as it passes through the diffraction of its own finite aperture. Proposals gather around the idea of a phased array, a field of many small emitters whose light is combined into a single beam by exquisite timing. If the array sits on Earth, it must look up through a sky that trembles, and so adaptive optics must sense the atmospheric ripples in real time and correct them by tilting and warping mirrors faster than wind can change them. If the array sits in orbit or upon the moon, the air vanishes and the stability grows, but the engineering burden shifts to building a structure the size of a city in low gravity, and to feeding it with power that must be stored and released in pulses of stupendous brightness. The sail itself becomes a material riddle. It must be large in area yet almost without mass, perhaps only a few grams spread across tens of square meters, formed from thin sheets that act as dielectric mirrors at the chosen wavelength, their layers tuned to return light with very little absorption, so that heating remains below the threshold where the film would soften, wrinkle, or tear. Graphene and other carbon lattices promise strength at low weight, but pure absorption would cook them, and so designers imagine stacks of transparent layers that act like a mirrored skin without the penalty of heavy metals. The sail must be shaped not as a flat plate but as a gentle cone or a curved bowl, so that if the beam drifts to one side, the resulting pressure nudges it back a passive stability, akin to a marble in a shallow dish. The rigging in this case is not rope but tension set by rotation, the sail spun to stiffen it against flutter, the way a coin steadies when twirled. The challenge is that spin and beam pressure can couple into wobble, and wobble can grow if the timing of the beam's corrections falls out of step with the sail's natural modes. The beam itself must be held on target with a precision measured in millionths of a degree for minutes at a time. As the sail accelerates, the reflected light shifts in color by Doppler's rule, and the mirror must still reflect well at that shifted color, or else heating will rise just as push is needed most. As speed climbs, the sail begins to feel dust and gas as sand in a gale. Micrometer grains at tens of kilometers per second can pit and tear. Even neutral atoms that strike a charged sail can ionize and build additional charge, so the craft must carry a way to bleed electrons or to discharge periodically without letting arcs scar the film. The forward edge becomes a sacrificial shield or a replaceable film, and the path chosen through the heliosphere may prefer directions where dust counts are lower. Engineers must also answer how to mount a payload to a sail that wants to be nothing but surface. The answer is often to make the payload minuscule, a chip that carries sensors, a clock, a small camera, a radio, and a thin coil that can interact with magnetic fields. The dream leans into a swarm, many tiny sailcraft launched in a volley, so that losses are acceptable, and statistics ensure that some survive to tell. The point of such gram-scale scouts is not to carry habitats, but to reconnoitre the path between stars and to bring back images and fields, the first quick notes of a tune to be played later by heavier ships. As the beam fades and the sail departs, the problem reverses how to break near another star with no companion array to push back. Concepts include flipping the sail and letting the target star's light serve as a brake or photon parachute that steals a fraction of speed with each reflected wave. Another idea is to unfurl a loop that couples to the interstellar medium as a magnetic sail trading momentum with the thin plasma by pushing on its field. A more daring plan uses a planet-sized magnetosphere as a brake grazing past a target world, so that dragon fields slow the sail enough to leave it in a bound path for a short study. Each of these tricks is limited, and none can stop a craft that began at a few % of light speed entirely, but each can shift minutes into hours at a target enough for a flyby that observes more than a single flash. The economics of a beamed system carry their own mysteries. Building an array of lasers or microwave emitters with total power in the gigawatt range requires a supply of energy as steady as a river, and electrical hardware that can switch that energy into light with efficiencies that approach ideal. Earth-based arrays can draw from grids but must cope with weather and with the politics of safety, because a beam that can push a sail can also burn a line through sky if mispointed. Lunar or orbital arrays avoid air and offer continuous access to cold for radiators, yet they demand launch of components by the thousands and robotic assembly in environments where dust is abrasive and where thermal cycles fatigue metal. There is an argument that such arrays, while expensive, would be reusable infrastructure serving not only sail launches, but also power beaming to craft throughout the solar system, uplinking energy to bases on the dark sides of worlds, and acting as astronomical instruments when not firing. This dual use appeals because it turns a single purpose into a network. The path to smaller, nearer arrays likely begins with microwave frequencies where the technology of phased emission is mature and the travel through air is slightly kinder, then steps to shorter wavelengths that offer tighter focus and thus longer ranges. At each step, control improves. Phased arrays can steer beams without moving parts by adjusting phase across tiles, and can even correct for broken elements by shifting weight to neighbours. The sail likewise evolves across versions, with early models tested in low Earth orbit, then farther each hop teaching how charging, heating and beam riding combine in practice, rather than in simulation. The cumulative lesson from these studies will decide whether the vision of faint, fast scouts is practical. It is a vision with romance, but also with rigour. The numbers demand a beam held steady on a target only a few meters across from a distance of thousands of kilometers. The sail must reflect almost all of the power while absorbing so little that its temperature stays far below its softening point. The payload must tell its story home from distances where light takes years to return, through antennas so small they fit on a postage stamp, and through backgrounds of cosmic noise. If these demands can be met even partially, the reward is speed that no rocket can match without fuel it cannot carry. The prospect of a small fleet of sails, each the mass of a songbird sprinting toward a nearby star and reporting back decades later, changes the timescale of interstellar reconnaissance from the age of cathedrals to the span of a career. Such sails would not carry people, but they would carry questions, and the answers would feed the next designs. The mystery that remains is whether light can be made to behave as a stable wind rather than as a wild glare when used at such scales, and whether materials can be made that act as perfect mirrors without mass. The path to that answer winds through laboratories that print nanostructures, through test ranges that paint beams across thin films, through mountaintop arrays that learn to hold coherence against a living sky. Beamed sails turn leaving into a matter of building a lighthouse bright enough and a mirror light enough that the two can talk across the distance where air thins and where momentum becomes the only true coin. In that conversation, each photon speaks softly, but there are many, and they can add up to the first deliberate steps between stars. To leave and keep living a ship must become a small world that carries its own weather, its own seasons and its own quiet shields. Radiation sets the first terms. Inside the heliosphere, the sun's cycle modulates the rain of cosmic rays, but beyond the heliopause, the galaxy speaks without filter, and high-energy particles arrive with a steadier, harsher tempo. Bursts from the sun still matter because their shocks travel outward for years, yet the background becomes the chorus of distant remnants and quiet accelerators spread through the Milky Way. A habitat answers with mass and with fields. Water, polyethylene and other hydrogen-rich materials slow fast nuclei more kindly than metals, and so tanks, food stores and waste reservoirs are wrapped around sleeping quarters to create a storm shelter. The shelter is a womb built of necessities, a place where alarms would guide the crew when a wave is forecast by heliophysics, monitors closer to the sun, or by sensors that sniff a rise in energetic particles. Active shields tempt the imagination. Superconducting coils could inflate a magnetic bubble that nudges charged particles aside before they touch walls, and hybrid systems could drive a faint plasma around the hull so that the bubble has something to push against. These methods carry penalties in power, complexity and mass, and they must be quiet enough not to twist the ship with their own fields or heat the habitat with waste. Yet the logic remains. A thin field that reduces the highest energies only a little could still cut total dose sharply over years, and every fraction matters when the trip lasts decades. Micrometeoroids and dust set the next terms. The heliosphere already throws grains at high speed, and the interstellar medium adds its own slow flux. A Whipple shield, a thin sacrificial skin set off from a main wall, turns a tiny stone into a cloud that spreads before it reaches the pressure shell. The ship wears such skins like scales in the direction of motion, and places critical systems behind multiple layers offset to avoid straight paths. Windows shrink or vanish, replaced by cameras and displays that paint a sky without inviting a crack to grow. Antennas retract into alcoves during storms of dust predicted by forward radar or inferred from rising impacts on leading sensors. The hull is not only protection, it is plumbing. Air loops wind through it, carrying heat to radiators that unfold like dark wings to throw waste energy into night. Those wings are broad because in space heat leaves only by light, and the ship must shed kilowatts day after day without sprays or streams. Their surfaces face away from thrusters and from any engine plume to avoid erosion, and they are watched for pinholes and for thin frost, where a trace leak could betray itself. Life support becomes a garden of cycles. Carbon dioxide is scrubbed and turned back into oxygen by devices that bind and release gases as they warm and cool, while water is reclaimed from air and waste until each molecule has passed many times through lungs and leaves. Plants, algae and bacterial biomes add a slower layer that smooths spikes and supplies fresh food and colour. A narrow corridor planted with greens and lit in cool tones becomes both a bioreactor and a path for walking. The garden calms because it grows, and its slow feedbacks teach patience. Seeds and starter cultures sleep in shielded stores to renew the system after a shock. The ship carries a small chemistry lab to make simple medicines, and a printer that can build gaskets, clips and brackets from resins and recycled plastics. When a hinge grows stiff, a part is drawn from a library printed and fitted by hands that have learned maintenance as ritual. A digital twin of the ship runs in silence behind the scenes, predicting when pumps will tire, and when filters will clog recommending swaps before failure rather than after. A slow voyage stretches human minds as much as machines. Days can braid into sameness unless the habitat lays out rhythms. Light follows a 24-hour arc, then bends into a holiday of a longer dusk once a week to mark time. Rooms change their hue by subtle rules, so that memory associates colour with task: green for exercise, amber for reading, blue for sleep. The ship keeps a shared log that records not only faults and fixes, but also small observations: the first frost on a radiator after a trajectory correction, the moment a distant flare was felt in the particle counts. These entries become the story that keeps purpose awake, while speeds and distances grow beyond easy feeling. Torpor hovers at the edge of speculation. Experiments with induced low metabolism in animals hint that a human crew might one day sleep in gentle cycles, lowering body temperature and activity for weeks at a time under careful care to reduce supplies and strain. The risks are many: clotting muscle loss, confusion on waking, and the unknown of cumulative effects after multiple cycles. A ship that relies on such sleep would need protocols for staggered watches and for medical equipment that can handle slow bodies. Even without deep torpor, crew rotate through periods of solitude and company, through exercise that prints artificial gravity into bones and hearts by steady forces on a wheel. A habitat that spins to make a fraction of Earth's pull spreads mass into a ring tens of meters across and hangs cabins along its rim. The radius is chosen to keep the perceived gravity smooth and the spin slow so that bodies do not sway, and the inner hub holds labs and storage that welcome low-gravity work. Safety hides in layers. Systems that keep air moving and water clean are doubled or tripled, and their lines cross so that one failure does not starve a room. Cables run in separate conduits, fire breaks interrupt studio-sized volumes, and sensors map every breath of current and every touch of heat. The ship assumes it will be far from help for stretches measured in hours at first, and then in days, and then in years as light time grows. Its procedures reflect that loneliness. Autonomous software can diagnose and even repair in small ways. Robots with soft hands fetch and hold. Tools teach with projected guides that draw a faint glow where bolts sit, and annotate steps with simple icons, a language that helps when tired minds falter. Medicine becomes a quiet workshop. There is no hospital to divert to, and so the clinic carries scanners, a freezer of blood and plasma, and a small device that can print tissue patches to help a wound close. Drugs age in radiation. The pharmacy tracks their potency and makes fresh batches for common needs from base chemicals. The crew keeps up with small drills not to chase fear, but to make calm actions automatic: seal a leak, isolate a fire, treat a decompression sick patient. The galaxy will not try to kill them, but will not save them either. The purpose is to meet the indifferent medium with skill. Communication stretches. At first, a question sent home returns in minutes, then in hours, then in days. Advice from Earth lags beyond utility, and so the ship becomes a society with authority distributed among crew and among machines. Decisions are documented, dissent is recorded, and outcomes are reviewed with humility because the next choice will also be made alone. Culture on board is not decoration, it is glue. Music plays, stories are told, games are invented that require slow attention, and an archive of earthly scenes rotates on screens that show forests, storms, and city streets to remind the senses of rich motion. The question of shields returns in a different form: how to shield minds from drift. Purpose is the strongest barrier, but design helps by making each day bear a shape, and each week involve a task that only the team can do. The ship is not only a vehicle, it is a laboratory, reading the interstellar medium a telescope whose baseline grows a testbed for systems that will fill the next generation of craft. Its results are the thread that ties crew to home across the long slack of light time. Leaving is thus not a jump but a practice of care. The systems that hold air, water, and heat in balance are as sacred as propulsion. The shields of mass and field keep the rain of particles at bay, while dust shells blunt the sharp wind of grains. Gardens and loops turn waste into food, and light into rhythm. Sleep, whether nightly or in longer cycles, is designed, protected, and honoured. In this layered quiet, the mystery of distance loses its bite, and the ship becomes what it must be, a small and stubborn world that moves. Before a ship carries people between stars, smaller craft can go first to taste the water. Beyond the surf, fast probes that race to hundreds of astronomical units and read the interstellar medium directly. These interstellar precursors are not fantasies. They are mission drafts on drawing boards and studies that weigh mass against speed power, against lifetime, and knowledge against risk. The goals are sharp. Measure the pristine spectrum of galactic cosmic rays outside solar modulation. Map the shape of the heliosphere in 3 dimensions by leaving along different bearings upwind toward the interstellar flow, crosswind where draped fields may be taut, and downwind into the long tail, where the solar wind streams away for hundreds of astronomical units. Sample neutral atoms and dust to learn the chemistry, temperature, and speed of the local interstellar cloud. Read the magnetic field directly and track how it bends around the heliopause. Turn back for a moment to stare at the sun's bubble and build global images from afar as a traveller on a dune looks back to see the outline of the shore. The architecture of such a probe begins with speed. A launch that falls toward a giant planet for a gravity assist, then continues to a close pass of the sun for a true Uberth burn, can leave the inner system with a velocity that reaches many tens of kilometers per second. With careful timing, a chemical or nuclear thermal stage that fires for only minutes near perihelion can convert that dive into an escape that coasts at several astronomical units per year, far faster than any craft now outbound. A less extreme but still potent plan trades the solar dive for a deep pass behind Jupiter, and perhaps Saturn, accepting a smaller final speed in exchange for reduced heat load and complexity. The second pillar is power. A craft that runs for decades cannot sip sunlight beyond the inner system. It must carry a radioisotope power system that turns the slow warmth of decay into electricity for instruments and for communication. Newer thermoelectric materials and dynamic conversion schemes promise more watts per kilogram than earlier generations, but even with gains, the budget is tight, and every instrument must justify its draw. Waste heat becomes a quiet ally, keeping propellant lines warm and preventing detectors from freezing, yet the thermal glow must be shaped so that it does not bias sensitive accelerometers or confuse instruments that measure faint infrared backgrounds. The third pillar is communication. At hundreds of astronomical units, the beam back to Earth spreads thin. Large antennas and high-power transmitters help, but they pull on mass and on the power ledger. Optical links offer a way to trade mass for precision, sending narrow beams of light that photon counters at home can catch. A laser the size of a shoebox aimed by a star tracker that reads not only stars but also bright pulsars as beacons could write data directly onto arrays that sit on mountaintops or ride in orbit. The pointing must be exquisite, and the craft must manage the slow jitter of its own structures as they flex under thermal cycles. Even so, the reward is a data rate that does not fade to a whisper as quickly as radio would. Instruments form the fourth pillar. A plasma package counts ions and electrons, measures temperatures and waves, and senses the direction and strength of the magnetic field. A neutral atom sensor drinks from the stream of interstellar hydrogen and helium that slips through the heliosphere, records angles and speeds, and passes out the distribution of energies. A dust detector listens for taps and measures the charge and momentum of grains. A cosmic ray telescope tallies high-energy particles from outside and separates species by their tracks. A wide-field imager for energetic neutral atoms looks back to paint the heliosphere as a glow revealing the ribbon where draped fields align, and watching it change as the craft's viewpoint shifts by hundreds of astronomical units, giving true parallax that turns previous two-dimensional maps into volumes. A simple camera faces forward to catch any faint glow from the interstellar medium and to record the starfield for navigation tests. The mission plan threads chances for extra science along the way. Before the deep outbound coast, the probe could cross the Kuiper Belt and fly by a dwarf planet, or a cold classical object taking images and spectra that reveal composition and texture. It could pass above or below the plane to sample latitudes where the solar wind and fields differ. It could angle downwind to sniff the heliotail and see whether it is a long comet-like stream or a shorter blunt plume. Each choice trades final speed for encounter geometry, and the design must decide whether to privilege the interstellar measurements or the nearer worlds. Navigation blends precision and patience. Beyond the reach of frequent tracking passes, the craft will rely on an onboard clock that holds time to within microseconds over years, star trackers that read the fixed sky, and when possible the timing of pulsars to refine position, like a cosmic global network. Tiny thrusts from cold gas or electric microthrusters trim attitude and occasionally correct course, guided by a model of non-gravitational forces that includes thermal recoil from the warm power system. The leftovers of the Pioneer anomaly become a coefficient in the tables, not a surprise. Autonomy is not a boast, but a necessity. When the light time grows to days, the craft must choose safe modes, wisely execute long sequences without uplink, and store data until the geometry brightens for a downlink pass. It must test and recalibrate its sensors as they age, compensate for declining power by cycling instruments, and protect itself during dust storms that it infers from rising impact counts. It must be gentle with its reaction wheels and thrusters to last for decades without servicing. There is a case for more than one probe. A pair launched a few years apart along different bearings would turn a single line of knowledge into a stereoscopic view. An upwind craft would feel the hydrogen wall and the heliopause at their most compressed. A crosswind craft would map the flanks. A downwind craft would chase the tail and decide whether the heliosphere closes in a sheath or leaves open pockets where interstellar plasma mingles. Their combined measurements would solve for asymmetries and for time variability, separating the breadth of solar cycles from the wrinkles of the local cloud. There is also a case for layering scales. Alongside a flagship that carries a full suite and a large antenna, a volley of small scouts could ride piggyback and be released on diverging paths. Each chip-scale probe powered by a tiny radioisotope source, or by a thin film sail that rides sunlight for a while, would carry a minimalist package to count particles and to flash home when geometry allows. Losses would be expected, but survivors would add dots to the map, a constellation of points that show gradients and structures that a single line would miss. Science beyond heliophysics would hitch a ride. Far from the sun's dust, the sky darkens in infrared, and optical bands and a cooled detector could measure the extragalactic background light more cleanly than any near-Earth telescope testing models of how many faint galaxies there are and how early stars lit up the universe. A tiny radio antenna could measure the whisper of the cosmic microwave background dipole from a vantage free of local clutter. A clock aboard could compare its tick with Earth to search for minute drifts that might hint at physics beyond known forces over long baselines. These are gentle riders that do not distract from the main goal but amplify the return. The cultural logic of such a mission is strong. A craft that reaches 200 astronomical units within a human generation would give a panorama of the heliosphere from the outside, while many who launched it are still alive to see it. It would lay down the first reliable distances and densities for the local interstellar plasma, constrain the draped magnetic field, and measure the dust that a crude ship would one day face. It would convert models into maps. It would also practice the disciplines that leaving demands propulsion, that treats gravity as a partner power systems, that hum for decades, communication that works at the edge of silence, autonomy that does not fail when counsel is far away. In tasting the ocean beyond the surf, such precursors would not yet cross to another shore. They would stand in the foam and drink the air turn and speak of currents and weather. The question of whether we will ever leave becomes less abstract when the first scouts report. The edge turns from a line on a whiteboard into a landscape with costs, routes, and seasons. The mystery does not shrink. It sharpens, which is the kind of progress that a long journey needs. Departure is a sliding idea because the stage itself is moving. The sun circles the Milky Way on a path that lasts hundreds of millions of years, drifting through patches of warmer and cooler gas, denser and thinner fields, and past stars that come and go like slow ships on a farther sea. The planets orbit within this motion, and the heliosphere breathes with the rhythm of the star and the medium around it. Even the constellations that a navigator trusts are not fixed. The nearest stars creep by fractions of a degree over lifetimes, and some of them swing close enough that their gravity and winds touch the outskirts of the sun's domain. In such a scene, to leave is not only to cross a boundary, but to choose which boundary matters, and for how long. A craft that passes the heliopause has entered interstellar plasma, yet it will still be inside the statistical shell of comets for spans that dwarf history. A craft that crosses the last gravitational whisper of the Oort cloud will have left the sun's direct claim, yet the galaxy will still tug on its path, and the echo of the sun's birth cluster will still be engraved in the distribution of distant bodies. The departure line therefore looks less like a ring and more like a set of nested shifting contours traced by different kinds of influence: magnetic, particulate, gravitational, and cultural. The first contour in plasma is thin and already crossed by emissaries. The second contour in family extends for light years and ages. The third contour in purpose is the one that humans set, and it may be the most decisive. Purpose is what turns a crossing into a migration rather than a survey, and turns a flight into a story that continues. The data gathered so far sharpen the question instead of dulling it. If the heliopause can sit nearer or farther by dozens of astronomical units depending on solar phase, and by hundreds depending on direction, then the success of a crossing cannot be measured by a single distance, only by the blend of conditions sensed. If the hydrogen wall can thicken and thin, then the first taste of the outside can arrive early or late. If turbulence and reconnection stitch the sheath in spots, then paths can be found or missed. These instabilities do not forbid leaving. They define it as a practice that listens. In such a practice, definitions become tools. A program might declare departure in plasma terms when galactic cosmic rays and interstellar densities match models of the local bubble, rather than solar modulation. It might declare departure in gravitational terms when the craft's energy relative to the Sun is such that no later encounter within the planets can return it. It might declare departure in family terms when the last significant perturbations from Oort cloud statistics fade below some threshold. It might declare departure in human terms when a habitat can sustain itself on the resources it carries without resupply from the inner system for a time measured not just in years, but in generations. Each declaration is honest within its frame, and none cancels the others. The mystery is whether any single frame deserves primacy, or whether leaving will always be many-layered. Changing stars add a deeper twist. The sun does not travel alone. It weaves through a neighborhood where stellar winds carve their own bubbles. When another star passes nearby in 1,000,000 years or in 10 million, its astrosphere may brush the outer skirts of the Oort cloud and slacken or tighten the flux of long-period comets. In the far future, the sun itself will age swelling through phases that change the wind, the light, and the pressure it exerts. The heliosphere will grow and shrink on timescales longer than empires, and the idea of a fixed edge will fade further. A civilization that spans such durations could choose to leave by weighting matching departures to phases when the door thins, or by engineering building engines that ignore the door's mood. It could choose to define leaving not by where the sun's influence ends, but by where community extends by the presence of stations, relays, and lights that mark a human archipelago spread across the outer regions. In that view, departure becomes a change in density rather than a crossing, a thinning out of familiar waypoints until only the faint glow of distant traffic remains. The rhetoric of first and last eases, and the language of continuity rises. There is a parallel in the physics. When a beamed sail races outward, it may cross plasma edges quickly, yet it remains tied to the beam for minutes that contain its whole acceleration epoch. The beam is a human tether made of light, a visible proof that departure is also connection. When a fusion-driven ship climbs slowly for months, it becomes a small world that must govern itself, and the line that matters most to its crew is the one between habitability and fatigue, between enough redundancy and too little. For them, leaving will be felt not in account of cosmic rays, but in the quiet confidence that systems can heal after a shock, and that gardens will still bear, and that time can be marked by rituals that give shape to long weeks. The unresolved prospects of interstellar travel gather around timescale. Travel at a few % of light speed can reach nearby stars in centuries. Travel at less than that can carry scouts across the outer system within lives, but turn stellar crossings into civic projects measured in generations. The pomp of a launch cannot carry a mission that long. Only social designs can. Archives must be fault-tolerant, languages must be resilient, and authority must adapt to distance. Perhaps an answer lies in swarms and in succession. A volley of fast light probes goes first to survey. A chain of heavier, slower habitats follows, each one a link that listens to the next and to the last, tightening error bars on maps and on methods. Alongside them, infrastructure spreads power. Beaming stations, hibernating factories, caches in the inner shell, and telescopes that can see the path ahead. None of these pieces alone is departure. Together they are a migration that redefines the question with each new reach. There are strange possibilities at the margin. The sun's gravity bends light. Far from the star, at a focus that begins beyond a few hundred astronomical units, the gravitational lens could magnify distant targets by huge factors. A mission that sits at such a focus could watch a nearby world across years, with a resolution impossible from near Earth, using the star itself as part of the instrument. That outpost would not have left the solar system in family terms, but would have left it in purpose, turning the periphery into a platform for seeing. There are also the long allegiances of biology. Perhaps engineered organisms will one day live within ships as partners, rather than cargo repairing materials fixing nitrogen printing enzymes on demand, and turning the hull into a membrane that senses and responds to the medium. In that case, leaving becomes ecological, a joining of machine and living cycles that can endure fluctuation and scarcity without constant intervention. The act of crossing then would be less about a line and more about robustness under change. The nearest stars tempt with their names: Proxima Centauri and its planets, Alpha Centauri A and B with their own likely worlds, Barnard's star and its ancient pace, Tau Ceti with a retinue that whispers stability. They are neighbours by cosmic measure, yet far by the pace of current craft. To reach them calls for engines that skim the edge of what materials permit, or for patience that remakes thinking about projects and lives. Between now and then, the path is full of honest work, mapping the heliosphere in volume, measuring the true spectrum of the local interstellar medium, learning how dust and fields sculpt the space between stars, and testing the closed ecologies that a ship will need. Each step reduces surprise, and each surprise that remains enriches the mystery rather than blocks it. In the end, the question in the title reads less like a challenge and more like an invitation to define departure with care. Will we ever leave our solar system? In plasma, yes, already. In family, not for a long time unless speed grows. In gravity, when the last whisper of the cloud fades on timescales that depend on engines and on will. In culture, when a thread of voyages is long enough that the edge, however defined, becomes a home border rather than a frontier. The most honest answer is that leaving is a verb ongoing, braided from climbs and crossings at many scales. It will not end cleanly, it will broaden. The open questions are the right closing: which definition of edge will guide design, which boundary will matter to a generation born aboard a ship, and which maps will they carry when the sky ahead is no longer the sun's? As the star moves and the galaxy breathes, the path will remain, and the mystery will remain with it, not as a wall, but as a horizon that walks away just fast enough to keep curiosity alive.